Recording in progress.
Never mind. If you can't see the screen and you're on Zoom, please let me know. So I've decided to split this review up into two separate parts because there's just a massive amount of content to regurgitate. Hopefully, it's not just regurgitation on the test. So today is really focused on everything you've learned for the first two midterms, exam one and exam two. And then tomorrow we'll go over the all of the biochemistry stuff like glycolysis, beta fatty acid oxidation. What else is there? The citric acid cycle. My goal here today is not so much to go through all the nuances and the intricacies. It's more just like a broad overview of everything we've done. You still have to, as much as this review may or may not help you, and a lot of people are not here. Oh well, you still have to study and prepare on your own. But we'll do my best, and I hope this is of some worth to you. And I am recording this, and I will post this on Learning Suite later today. Also, what am I thinking? I think it'll take about an hour, hour and a half for me to get through this first part of the material. And after that, I'll take questions. And if we're done early, we're done early. That's one thing we should learn from General Conference. If General Conference can end early, so can BYU classes and sacrament meetings. But before we begin, just a little bit of humor. This is probably how you're feeling right now with all the exams coming up. Or you could substitute have a job, get married, and have kids with take an organic chemistry exam. Anyway, let's go back to the very beginning of the semester, where we learned about carbonyls and specifically the stability of the carbonyl compounds. So really, we learned two different mechanisms or two different criteria for determining the stability. And there is a blank copy of this on Learning Suite if you want to annotate it as we go along. It's under my page at the very bottom. So the first thing we could look at was the stability of the leaving group. And the primary way we determined the stability of the leaving group was using pKa values. So better leaving group, the better leaving group we had, the more reactive the carbonyl compound was. So for example, if we look at this chart from the book, let's write out all the conjugate bases we could have if we did a nucleophilic substitution. So we had chloride, we have a carboxylate, we have a phosphate, which is really on the same level of reactivity as, there's a P in there, don't worry. We got the thioester, the ester, and the ammonia. Now, what are the respective pKa's of those conjugate acids? Well, HCl is like -3. Uh, acetic acid is like 2. Still want to spill that stuff on yourself. Phosphoric acid, oh boy. HPOO minus, O minus. That was pretty low. That was like 3. HS, I think that's like 9. These are on your pKa chart if you want to reference those. And NH4 plus is like 9. No, NH3. Ammonia has a pKa of 38. So you remember that the stronger the conjugate acid, the weaker the nucleophile or the conjugate base. So you can see here the chloride and the anhydride, they have very strong conjugate acids. Therefore, their conjugate bases are weak and therefore good leaving groups. Now, the other method we use to determine the overall stability of the carbonyl compounds was through resonance, whether or not we can stabilize lone pairs of electrons. And really what this comes in most useful is for explaining the difference between thioesters, esters, and amides. Because as you know, all of these have a lone pair of electrons. No, I don't want to do that one. They have a lone pair of electrons, which we can use to swing into the carbonyl. So we can pull it down, pull it up, pull it down, pull it up, pull it down, pull it up, and the respective resonance structures that we would obtain are R O minus, SR plus. For the ester, O minus. Why did I write O? Oh, because I meant to. So, I don't know if more people are going to show up, but they're lost. They're lost. Sorry, not that they're lost people, just that they're not taking advantage of the resources. Now, what this tells you, what this shows you, is that you can distribute the charges throughout the system. Now, the oxygen, there's no difference there. O minus, O minus, O minus. What is different is what atom is bearing the partial positive charge. So the thioester, even though sulfur is not a very not super electronegative, it's still a bigger atom and it doesn't have good electron overlap with the oxygen. However, it is still a better it's still a better carrier of that positive charge because it is much less electronegative than the oxygen. And let's compare the oxygen with the nitrogen. Which one's less electronegative? The nitrogen, yeah. So the N atom has a greater ability to hold the positive charge than either the oxygen or the sulfur. And for that reason, it adds stability to the carbonyl compound. Now, what's not in this chart is the aldehyde and the ketone. These are also reactive, but we can't use the same logic, so to say, because what pops off here is a hydride and a carbanion, both of which are extremely poor leaving groups. The reason that these are more reactive is because if you look here, there's less steric hindrance. Whatever aldehyde or ketone you have, the carbonyl, just the bare carbonyl, is easy to attack. Now it can't undergo additional nucleophilic substitution. We can just take a nucleophile and add one thing to it and one thing only. We'll get more into nucleophilic substitution in the next little bit. Yes?
There's someone in the Zoom waiting, right?
Oh, a lot of people are there. Hello, people. Okay, can you see it now? Zoom people, can you still see my recording,
Yeah.
my screen, whatever? Okay, that makes me feel better about myself. Okay, go away. I don't mean you. I mean the little pop-up in the corner. Okay. Well, oh well. Okay. The other big thing that you had to keep in mind was oxidation and reduction, because this allows a simple, a pretty accessible way to access the different carbonyl compounds. So the base one is just an alcohol. The secondary alcohol only has one option. We just oxidize it up using PCC or KMNO4. And we stop there because we have two different carbons attached. Now, the primary alcohol, we have a few more options. We can use PCC, bring it up to an aldehyde. And remember, you use this transformation a lot in synthesis. If you see an alcohol or if you see a ketone or an aldehyde, you should think, oh, I could have had an aldehyde before this. The aldehyde we can take up one step further and make it a carboxylic acid using a stronger oxidizing agent. What did I meant? CrO3. And that's as far as we can oxidize it. We can transform this into an ester using a Fischer esterification acidic conditions. We will go over that a little bit, but the reason I'm adding it now is because we can easily go from an aldehyde to a primary alcohol if we just reduce it with something like sodium borohydride. We cannot reduce the whatchamacallit, the carboxylic acid. Yes, sorry. Why? Because we have this acidic proton and it basically kills the reducing agent. But you can convert it to an ester, and from the ester, you can selectively reduce it to the aldehyde using the special diisobutyl aluminum. I don't remember what it is. Lithium. And very cold temperatures. And then from there, you can reduce the aldehyde using sodium borohydride. Our really powerful reducing agent is what? Lithium aluminum hydride, yeah. And it's a stronger reducing agent than sodium borohydride because it's bound to the lithium, because it's the lithium hydrogen bond is much stronger than the boron hydrogen bond. And I'll just make a note right here. Selective for aldehydes and ketones. This one does everything. So if you had to pick, those riddles where it's like choose a door and like you have to live here for the next 24 hours. Well, if you had a choice between two reagents to spill on yourself, choose a sodium borohydride, not lithium aluminum hydride. Of course, you shouldn't open those doors anyway. All right, and here's really the only place we did real organometallic chemistry. We have done a lot of that in the last couple of days. We'll do some of that tomorrow. But the organometallics that we need to keep in mind here are organolithium and the Grignard reagents. Grignard. It's German or something. How do we produce those? Well, we take the alkyl halide, we treat it with lithium or magnesium. We generate the corresponding base. Now, what you need to realize with organolithiums and Grignards is that these are very strong bases. So we can easily add them in a nucleophilic addition. Oh, wait, what did I want to say? These are strong bases, which are basically the equivalent of carbanions. So for these ones, you have to watch out for acidic protons. Is someone screaming? That's outside. So if you have an acidic proton anywhere in your compound, such as in an alcohol or a carboxylic acid, what do you have to do first? You have to eliminate it. You have to do a protecting group on the alcohol, or you have to convert that carboxylic acid to an ester. Now the other one, which was interesting, so we can take the lithium and we can actually we can treat it with copper. And we need two equivalents of the copper. Now this one is less reactive. simply because the copper, I wish we had a periodic table here. Simply because copper is a bigger metal atom, it can better stabilize the negative charge than the magnesium or the lithium. So because it's less reactive, it will only react with certain things like Michael product, like here, it'll add to the double bond end, and it will only react with the most reactive of carbonyl compounds. So for our intents and purposes, it really only will react with an acid chloride, anhydride, or an acyl phosphate, and it'll only do a singular addition. The Grignard reagents, however, with these particular things can do a double addition. So if you want a single nucleophilic substitution, use the organocuprate. If you want a double addition, use the Grignard or organolithium. Grignard and organolithium are basically the same reactivity. Same, whoops. So here, this is really what laid the foundation for all of our carbonyl chemistry. Because I'm trying to think too many things at once. The big reaction mechanism that we saw for several chapters was nucleophilic acyl substitution. And it all follows the same basic pattern regardless of whatever you have on there. So you have your carbonyl, could be an amide, ester, whatever. We take a nucleophile, add it on there, and we form the tetrahedral intermediate. Now, if R or R prime is good leaving group, we can swing the electrons back down from the oxygen and kick off one of the groups. And we actually regenerate our electrophilic center. Then we do it again, nucleophile, nuke, nuke. There you go. Now, all of these steps are reversible, but you have to take into account what your good leaving group was. So with this mechanism, you can easily go from, say, an acid anhydride to an ester or an amide, but using this mechanism, it's harder. It's easy to go downhill using this mechanism. It's much harder to go uphill, and in fact, you need special mechanisms to do that, or you need a catalyst. Did you have a question? Any questions so far? Good. Hopefully that means I'm doing well. So yeah, you've seen this reaction over and over again, but something you must absolutely keep in mind is the generation of the tetrahedral intermediate. And depending on whether or not you move forward in the reaction, there's always the possibility of chirality. Because look at this, you have carbon with 4 different groups attached to it. And so when we get to here, where we again generate the tetrahedral intermediate, there's always the possibility of racemic mixture of enantiomers. There actually is a way that you can generate specifically the R or S form. You need a special reagent to do that. If you want to learn more about that, take a 552 in the fall. Now, here's where we got into hemiacetals and acetals. So these are not carbonyl groups, but they do come from carbonyl groups. So the hemiacetal, we start with an aldehyde. Add an alcohol, and an acidic catalyst, because it really doesn't happen without a catalyst, in order to produce this. Now, the hemiacetal is a carbon attached to an OH and an OR group. You can take the hemiacetal and go one step further if you treat it with another equivalent of the same alcohol. Make sure I count my carbons. So an aldehyde you can convert to an ester, but an acetal, but it requires an extra step. Same with the ketone. Just treat it with acid and base. We get OH. We get OR. There you go. So the only difference between these two is whether or not we have a hydrogen attached or a carbon attached, which is what distinguishes between ketone and aldehyde. Now, we learned that there is a very special use for this particular group. What was it? Yep, it's a protecting group. And specifically, we used ethylene glycol. So we could generate something like this. So keep in mind, so it has to be the acetal because hemiacetals are quite reversible. They usually won't stay that way. Unless it's in a cyclic form, like with carbohydrates. And we saw a lot of that then, and that's biochemistry. So that's a tomorrow question. Anything biochemistry related, leave it for tomorrow. Now, something you may not, oh yes,
What specifically would it protect?
ketones and aldehydes. Ketones and aldehydes only. It will not work with any other carbonyl compound. It will not react with the ester or amide. Yes?
Are you getting to the two oxygen groups, like if that OH can't attack it, there's no ketone or no carbon attack. Like on the above, the right, one on the right.
This one? Yeah, it protonates the OH group and causes it to leave, and that can come back on again. So what happens, I'll write it down here. What happens is that this gets protonated. So that's OH2, which is a good leaving group. And this pair of electrons can come swing down and kick this off. So you've effectively regenerated the carbonyl. And from there, that's when you can add the alcohol on. So yeah, the hemiacetal does not contain a carbonyl, but with acidic catalysis, you can generate the carbonyl.
So with that protecting group, would you do it to protect aldehydes and ketones because it might be acidic condition? I prefer that. Or what is the purpose of protecting it?
So it doesn't do nucleophilic acyl substitution because aldehydes and ketones are some of the more reactive species. So like if you had an aldehyde or ketone with an ester or an amide and you wanted to do something to that ester or amide, acetal is the perfect thing to use. Okay. All right, moving on. So imines and enamines are really, this all has to do with nitriles. Before I get any further into this, let me just illustrate the oxidation and reduction. So the primary amine we can actually, it's exactly the same. It's pretty much the same chemistry as oxygen. And we'll get that more when we do the amine stuff. But we can easily oxidize that to an amine. Well, not really oxidize it, but you can think of it as an oxidation to the imine and finally to the nitrile. And that applies to primary amines. If you have a secondary amine such as this, you can oxidize it to the enamine, something like this. We can't actually transform amines into imines and amines into enamines directly. I just want to put it there so you can see. You'll see it later on because we can easily convert enamines and imines back to the corresponding imines or enamines. But the point you want to know here is that this allows you to transport nitrogen readily, easily. So if we have a carbonyl compound and we have either just ammonia or a primary amine, that converts it to this corresponding imine. NH and this. Now, the mechanism to form these compounds, is very much like forming a hemiacetal or a acetal. You need some sort of catalyst, like a small amount of acid, in order to move this reaction forward. Now, the only difference between imines and enamines is the type of amine you have. So imines form if you have a 0-degree or primary amine. But enamines will form if you have a secondary amine. So this is going to form, at first it will go through the imine, but what will happen at the very end of the mechanistic transformation is we'll deprotonate a hydrogen, bring those electrons down, and bring these electrons up. I forgot to add the other R group. So we'll get some. And these are also irreversible. No, I mean, they are reversible. And in this one, I added an extra carbon, so just ignore that. Okay. Any questions about that? Now, nitriles you do want to keep in mind. Let's make it benzonitrile. What you can do with nitriles that you cannot do with amines and enamines is you can hydrolyze it. The basic hydrolysis will turn the imine into a carboxylic acid. And from there, you have options to convert it to an ester and either alcohol, aldehyde, whatever. But you want to keep that as a useful synthetic trick because it does add one carbon to the chain. And I'll just mention this now. You can also take the nitrile and using lithium aluminum hydride and an aqueous workup, you can actually reduce it back to the primary amine. So if you want to make a primary amine, a nitrile is a good way to go. I was planning on going over this later. It's not easy to oxidize the primary amine to the enamine or the secondary amine to the enamine, but you can easily go backwards with a hydrogenation. See, it works the same way as a carbonyl. Usually you don't see that too much, but it is possible to do that. All right. So this is the other reaction you want to keep in mind. It's a very useful synthetic tool because it allows us to convert a carbonyl directly to a terminal alkene. In fact, if you see any terminal alkene in your synthesis, that is a good indication that you would use the Wittig reaction. The because it's German, but none of us speak German, so none of us really care. So before you do this, you have to prepare your Wittig reagent to get that to get that one carbon on there. Terminal alkenes are common, but you can do this with multiple reagents as well. But for this one, how we would prepare the Wittig reagent for this is first we start with methyl bromide or any other alkyl halide. We take PPH3, do an SN2 reaction in order to generate this PPH3 plus. Now after this, you have to treat it with a very strong base like sodium hydride or N-butyllithium. N-butyllithium is scary. What this will do is it will deprotonate this and come down here with positive charge. We have an extra orbital. So we have PPH3 with a double bond. You could also think of it as this through resonance. We generate an ylide. And personally, I prefer the ylide form because it's much easier to visualize what's going to happen. Because what happens is that the ylide will line up with the negative end will line up with the positive section of the carbonyl. This is partial positive, partial negative, and the phosphonium will line up with the partially negative oxygen. So it goes boom, boom, forms a need to zoom in a little bit. So normally you would look at this and say, what the heck? We can't form a tetrahedral. It's hard to form a cyclobutane ring. Well, what pushes this reaction forward is the formation of the oxygen phosphorus bond. The bond, the energy we release from forming that oxygen phosphorus double bond compensates for any energy we use to make that four-membered ring. And so what does that get us? Gets us back to here. Any questions about that? Is this a good pace? Slower, faster? Okay. Okay. So with carboxylic acids, there's really nothing very special about that. The only thing that's really different is that it has an acidic proton. And really the use of acidic or carboxylic acids comes from our ability to transform them into other reactive reagents. So like, do I have another slide on this? Well, if I need more space, I'll use more space. What we can do is generate this into more reactive intermediates. So the first thing, the most common ones are we can turn the carboxylic acid into an ester. And remember, make sure you have the correct alcohol you want to use. We can easily convert it into an ester. Well, not easily, but it works. NH2, duh, duh. This gives us a very direct way of making esters and amides. Though this is not a quick reaction, it does usually requires extra energy in the form of heat. Now, two other reactions you do want to keep in mind, and we've seen this in biochemistry a lot. Well, the first one, not so much. So take the carboxylic acid. If we treat it with thionyl chloride, that gives us direct access to an acyl chloride. And remember that acyl chloride is extremely reactive. Now the carboxylate, and this is the one you've seen in biochemistry all the time, especially with phosphoenol pyruvate, is we can take that carboxylate and treating with let me write out all the ATP subunits. No, there's still an oxygen here. This we can easily react with the phosphate, generate a pentavalent intermediate species. This gives us a DP and OPO. This gives us an acyl phosphate. And much like the acyl chloride, it's very reactive because we've now attached a good leaving group to that oxygen. Any questions about that? All right. Let's see. I put an extra slide there. I don't know why. All right. This you definitely have seen throughout all of glycolysis and the citric acid cycle, enolate chemistry. And what is it? It's all about the base. And what's so special about carbonyls? Well, they have an acidic alpha proton. The resonance with the carbonyl oxygen is what makes this all possible. Because we can take some generic base like sodium hydroxide, deprotonate that, and form this. Now, your first instinct, since this is a carbanion, negative charge on the carbon, you think, oh no, that's super reactive. Not so much. Why? Yeah, resonance stabilized. It's all because we have that carbon-oxygen pi bond on our thing. And we can form this, the enolate. Now, this is the more stable form. Why? Because it puts the negative charge on a more electronegative atom, but this one is actually more nucleophilic. So whenever you're doing this chemistry, it's going to be the carbon that attaches to something else rather than the oxygen, although there are probably cases where the oxygen can add on to something else. Now, I guarantee that one of you, at least one of you, maybe 20 or 30 of you, are going to forget about tautomerization, because tautomerization allows you to convert between the keto form, which is this, and the enol form, which is this. And this can happen under acidic or basic conditions. And it happens automatically. And if you ever see an enol, especially in some condensation reactions, you want to think, wait, I should tautomerize this first. And I'll show you an example of that later on. Now, how does that actually work? Well, in basic conditions, it's something like this. So let's just take hydroxide. It just deprotonates. And that's all there is to it. Now, it also works under acidic conditions, but it works a little bit differently. So the first thing that happens is that the carbonyl gets protonated first. The carbonyl oxygen gets protonated first in order to form I'll do H2O. Once we deprotonate that, once we deprotonate the acid, it actually generates a base for us. And we can use that base to deprotonate right here and move this electrons up to the carbon and the oxygen, and we generate our enol. Why is it called an enol? Why? Yeah. E comes from the alkene, and all comes from the alcohol. Or ene comes from alkene, and all comes from alcohol. Now, keep in mind that although the process is very similar, and to convert back to the keto form, it's just the reverse process. In the acidic conditions, you have it's protonated, and in basic conditions, the oxygen is not protonated. Now, which form is generally favored when we're switching back and forth? Yeah, the keto form is generally more stable than the enol form. Why is that? Because the carbon oxygen pi bond is greater in energy than the carbonyl, than the carbon pi bond. Now, the enol form in certain cases is actually more favored. So if it's just keto versus enol, keto is preferred. But when you have hyperconjugation, so say you have something like this, we can easily convert this middle group into an enol. And with all of this hyperconjugation between this double bond, 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 that actually favors the enol form. So hyperconjugation adds stability. Hyperconjugation adds stability. So if you have any sort of hyperconjugation, especially with the benzene ring, the keto form, the enol form will be preferred. Of course, you do want to keep in mind that this reaction happens readily. So in most of your condensation reactions, you'll actually generate an enol, but it can immediately convert to the ketone or aldehyde equivalent. And yes, this only works for ketones or aldehydes, not with esters or amides. Yes,
What are the orbitals that are being hyperconjugated?
it's all the p orbitals. So the C oxygen. So for hyperconjugation, you have to have alternating double bonds and single bonds. The double bonds have empty p orbitals. And all the electrons are happy floating around here. Well, that looks like a monster, doesn't it? But you get the idea, right? It allows the electrons to delocalize. If you can ever spread out electron density, it's a stabilization factor. All right. Now the big thing that we saw with
What's the thing with the sigma and pi of the last one? Because I thought that was a hyperconjugation.
yeah, so this right here, that's just a simplified version of it. What's actually overlapping, yeah, it's the pi star and the sigma hyperconjugation. It's overlap between pi star and sigma bonds. So you have to have this particular pattern in ooh, that's not good handwriting. I've asked this to my section whole time, is my handwriting better or worse than Dr. Price's? What's the answer? Is that sincere, or are you just saying that because that's what I want to hear? Anyway, you need to have this pattern to a significant extent to have enough hyperconjugation to favor the enol over the keto form. Make sense? All right. So what we saw with this is a lot of substitution reactions. And we'll go over some, let's see. We'll go over some caveats with enolate chemistry later, but I'm just going to make it pretty simple for now. So substitution reactions, these all follow an SN2 mechanism. So if we take this, just do a sodium hydroxide. There are the 2 alpha hydrogens there. I will get into that later. We can generate this enolate, and I prefer just to leave it like this, not deal with the resonance. This can easily react with an alkyl halide, primary alkyl halide, or anything else that's suitable in an SN2 reaction to form this. And this can repeat itself again because we have a second alpha hydrogen. Now, something I don't think we went over a lot is the fact that we can add a halogen to that methyl ketone. And this one really only works for methyl ketones. So if we generate our enolate like this and react it with bromide or chlorine, I'll stick with bromine, we can actually form this. And if we do that enough times, we can actually generate, I don't remember what this is called, but it's this tri-halo species. And this, Br minus. This is actually a good leaving group. Even though it's a carbanion, the 3 halogen groups stabilize that negative charge through an inductive effect. So this gives you a good leaving group. So you can easily react this with some other nucleophile in order to get something like this. But this reaction only works for methyl ketones. Why is that? Because the methyl group has 3 alpha hydrogens, allows us to do 3 substitutions to generate the leaving group. If it's just 1 halogen or 2 halogens, it's not good. We use bromine a lot in synthesis, but it is a very nasty chemical. So don't sniff it. All right. So the malonic ester synthesis and the acetoacetic ester synthesis are really they're really both the same thing, just different starting materials. A malonate is when we have a diester connected by, I'm not sure if it's a methyl or a ethyl group, but it's the same point. The point is you have an alpha hydrogen wedged between 2 carbonyls. And because it's between those 2 carbonyls, this is extra acidic. And really, it's the same idea as this, the basic substitution reaction, except it's just more acidic. That's the only reason why it's special. So to protonate it with a base, generate this intermediate, react it with some generic alkyl halide, make sure I count my carbons correctly. 1, 2, 3, 4. And we can undergo this substitution again if you do the same thing with an additional equivalent of the base and the alkyl halide. let me do the acetic acid synthesis before I do anything else. Before I show you the whatchamacallit, the decarboxylation. So again, this is the same thing, except instead of having that extra ester, it's just a ketone. But again, it's still between the two oxygens. So these hydrogens are still extremely acidic. So again, treat it with base. Form the intermediate. React it with an alkyl halide. Get this. Now, with both the acetic ester and the malonic ester synthesis, we can actually do a decarboxylation. So if we hydrolyze the ester, wish I had a little podium here, but there isn't one. We can hydrolyze that in order to make a dicarboxylic acid or just the beta keto acid. I'll point this out where I'll point out when you do the biochemistry tomorrow, I will point out where the organic chemistry comes in. Because what is biochemistry? Just applied organic chemistry. Whatever you do, you probably won't ever draw an arrow mechanism again because most of you are pre-med, right? Or you're doing something medical. It'll never go away, but if you ever do anything biology related, chemistry will be with you for the rest of your life. Now, why do I bring this up? Now, why do I bring the carboxylation up? So you notice here we have CO2 sitting around. If we just heat this up, that CO2 will not magically, but let's pretend it's magical. It'll just swap off that it'll swap off that carbon. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That will leave spontaneously, and then the malonic ester. Now the acetoacetic ester. So heat triangle means heat. I guess chemists are not really that creative. 1, 2, 3, 4, 5, 6, 7. So the reason why this is important is you can see that this right here, that's an extended carboxylic acid. And so this and this one as well. This is an extended chain ketone. So if you want a longer carboxylic acid or a longer ketone, malonic ester and acetoacetic ester synthesis are useful mechanisms to get there. They're also useful for this. Notice what group we created here. Whoops. It's a beta keto acid. You do not have to do the decarboxylation. It's just there as an option. And here we have the 1,3-dicarboxylic acid. Yeah.
So like, look at the calculus. I'm trying to remember, it's only gonna add like the number of equivalents it gives us.
Yeah.
Actually automatically add two equivalents. Unless it says there's two.
Exactly. So yeah, you have to have the right number of molecules to move forward.
And
Yes.
On that. Is that with all like carbonyl compounds, whether it's an ester, ketone, we just keep doing it with as many equivalents, or does it change?
No, it's just as many equivalents as you have. But remember, the enolate chemistry only really works with ketones and aldehydes. If we do an ester, so I mean, the ester does have the possibility of being deprotonated, but it's much less acidic. is so much less acidic that it's not really useful synthetically. Why is that? Well, if we generate the carbonyl, if we generate the carbanion, you notice we have two lone pairs competing for that empty pi star orbit. So this can still happen, but it's much less so because we already have resonance with this extra atom. Yes, Max.
In the melodic ester synthesis, if you made that, could you like eat that and metabolize it? The carboxylic acid, it's like a bad acid if you do. Yeah.
Yeah, you could. You could. Okay. Any questions for enolate chemistry? All right. Now we're on to chapter 18. So this is more of the same theme. It's still enolate chemistry, but now it's a different application. Because now it's not just now we're not just doing a substitution at that alpha hydrogen. We're now attaching on another carbonyl compound. So the standard reaction is just the aldol reaction. What does aldol stand for? Yes. Aldehyde and alcohol. No. Aldehyde and alcohol. Are we alcoholics? I hope not. So, or ketone. So the standard aldol reaction is we just take a simple ketone like this, for example, deprotonate it to generate our enolate, and then we'll just add to some other carbonyl compound in our solution. If it's the same thing, it's a self-condensation. All of these we call condensation reactions because we are reducing the total number of molecules we have 2 to 1. So that comes up. So this one you have to be a little bit careful about because you always have to add an extra line for your new bond. 1, 2, 3, 4. And then this will pick up a proton in the aqueous workup. And if you want to take this reaction further, you can actually do a beta hydroxy elimination. Just have to treat that with more sodium hydroxide. That'll pull off this acidic proton and cause this hydroxy group to leave. How do I draw that? You can stop here or here. This is the beta hydroxy ketone. And this is the alpha beta unsaturated ketone. You can stop at one or the other, but with this one, you have to treat it with an excess of base and probably heat it up a little bit. Yes.
Is that one the E1C?
Yeah, this is the E1CB mechanism. It's very much like I'm drawing it like E2, but it doesn't happen like E2. That's just the easiest way to see how the electrons move. Okay. Now, the Michael addition is a special type of aldol reactions. These are all different types of aldol reactions, but what's different is what you're adding to the what molecules are involved. What color should I use? Any color?
Purple.
Do I have purple on here? Yes, I do. Democracy. So the Michael addition involves adding to an alpha beta unsaturated ketone or aldehyde, which is simply this. this or the corresponding aldehyde. Now you remember that the ketone by itself is electrophilic. But because we have that extra pair of electrons just sitting there, we can also, oh boy, we can also make this resonance form. So we have two carbons that are electrophilic. And this one right here is the thermodynamic product. Or it'll form the thermodynamic product. Why? Because it's a more substituted alkene. So this involves taking an enolate and adding it directly to that position, the fourth position, or we could add it over here, whatever floats your boat or whatever pushes your electrons. We push electrons. Could we push buttons in here? Anyway, do this. O minus O. We have the new bond. Okay, we have this. And be careful. Whoops, I need to make that minus a little more convincing. This is one case where tautomerization will happen directly. So tautomerization. And I remember that I can do copy and paste. So move the double bond up. And there we have a 1, 2, 3, 4, 5. So the result of this is a 1,5 dicarbonyl species. Okay, any questions about that? If you're ever struggling to see it retrosynthetically, I would just take an example, like a simple example, draw it in the forward direction, and then work backwards from there. Okay. Now, the Claisen condensation is also an aldol reaction, except this happens between two esters. Now, with this one, you do have to be, so yes, you can do enolate chemistry with esters. And usually it's condensing with the same ester. So we'll just deprotonate this. And with this one, you actually have to be very choosy with your base. You have to use OR minus. You have to use the conjugate base of this. Why is that? Because you could add the OR minus, could easily add to your ester and eliminate that OR group. But if it's the same OR group, it doesn't make any difference. So yeah, you have to use the this and this have to match up. Otherwise, you'll get a mixture of products. So this will simply attach to another equivalent of the ester in solution. It'll add right there. Let's see. O minus OR. Of course, we do aqueous workup. Copy. And that's OH. Now, what's common with this reaction is you notice we do have a hemiacetal in there with the OH and the OR group. What usually happens is the same thing as with the aldol elimination. to make an alpha beta unsaturated component is, again, we still have OR minus. It'll take off this proton, pull this down, push this off, and we get something like this. Probably not drawing it very well, but you get the idea. Yeah, you generate that as your intermediate or as your final product. Any questions about that? If you ever have a beta hydroxy group, you can always do the elimination with the ketone lying around. All right. Okay. Robinson annulation. This is a tricky one because it involves multiple aldol reactions. It starts with a Michael addition. So say we take this enolate right here, that's much more acidic. We add to this carbon right here, pull it up, grab a proton at some point. Michael. Michael addition. One, 2, 3. 1, 2, 3, 4. Then we'll re-tautomerize. Here's another case where the tautomerization just happens automatically. Now for this, the only thing that this is going to, the only way this will work, at least under simple conditions, is if we form a 5 or 6 membered ring. So whatever the result of your Michael addition is, you have to look at all the different alpha hydrogens and determine where you're going to form a 5 or 6 membered ring. So if we start here, for example, if we go 1, 2, 3, 4, 5, 6, where it can attack the other carbonyl, that's an option that can work. We also have to check the other ones because we could go here or here, but those are both the same. 1, 2, 3, 4, 5, 6. That could happen. The final one is where you have a H atom right there. Let me do that in purple. 1, 2, 3, 4. That's not going to work so well. So you do have some options. I'll do the end one to show you how it works. So we have this, say we generate that enolate, and we attack right there. I'm going to skip some steps. But the thing you want to do here is draw out the ring that you're going to form and you want to label your carbons. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And then you want to draw that other hexagon over here. 1, 2, 3, 4, 5, 6 to make it easier to determine what you're adding together. So on carbon, so let's see. Here, I'll just erase this for a second. Or maybe I should change my numbering so it's a little more consistent. Yeah, well, no, you can deal with it. So let's see, what was on carbon 1? Nothing, but we added it to this carbon 6 over here. And obviously that's the case because there's a new bond. On carbon 6, we add a hydroxy group, or what becomes a hydroxy group. Between carbons 5 and 6, we have that huge extra ring. So let me erase that 6 and put it inside. Does this make sense how I'm labeling the ring and putting all the groups together? And of course, on this one, Wait a second. Yeah, on this particular ring, that's where the other carbonyls are coming off. Except there's no carbonyl right here because that became the hydroxy. So there's our other hydroxyl group. Huh, I flipped everything upside down. That's why it's confusing. Let's see. What else is there? Carbon 4, carbon 3, nothing attached to that. 2 has the ketone on it. So that makes our final product. This. Is that our final product though? No, because we can still do the elimination. So here again, you have to be careful. You have to look for all the hydrogens to do your E1CB. So if we do it from here, and let me make this a little smaller. If we do it from this first hydrogen, oh yes, I still have copy and paste, yay. No, not gonna use it. Now I'm gonna use it. So if we go from this first hydrogen, where do we form the double bond? Right here. If we go from the second one, whoops, we'll form it right there. If we go from the final one, we'll form it right here. So as you can see in all of these, except for the first one. Wait. This first one we actually wouldn't form. Oh, wait. How do I want to say this? So we have a possibility of forming all three of these products, yeah? But why wouldn't we do that first one as opposed to the other two? Yes?
One is
Yeah. Well, the answer I was looking for was it doesn't have hyperconjugation. But you're right, it's not acidic enough. So it wouldn't form this one. Now it's a toss-up between between 2 and 3 because we do have hyperconjugation in both cases. And it's but you look at the stability as well. This one right here is a tri-substituted alkene. This one right here is a tetra-substituted alkene. Which one's more stable? Yeah, so this one right here will be your major product. Okay, hour and 15 minutes. We're making good time. All right. Any questions about those reactions? All right. So with enolate chemistry, you have to be very careful simply because you have so many alpha hydrogens just flying around, which is where we introduce the idea of kinetic versus thermodynamic control. So if we want to put a substitution here, we have to use LDA. Why? Because it's a big, bulky, strong base, and will generate this enolate. If we want to put the enolate on the other side, right here, we just use sodium hydroxide or something of similar strength. The reason this is significant is because this is the kinetic product. Why? Because it's LDA is big and bulky. It wants to get to the less substituted side. And this one right here is the thermodynamic product. Because if we look at the enolates in the tautomerized form, you see that this one is a more substituted alkene. Now, whenever you're doing any aldol reaction, you want to label all of the alpha hydrogens, especially if you're doing the Robinson annulation. Because see, that's what made this trick problem a little more trickier. We had multiple sources of alpha hydrogens. So let's just take something. I'm just making up this molecule. No, I didn't want to do that. So let's see, how many sets of alpha hydrogens do we have in this molecule? 1, 2, 3, 4, 5, 6. So yeah, that would not be good to do in a reaction. But you can, if you do have multiple alpha hydrogens, you're always going to react with you're going to deprotonate the most acidic one. So with this hypothetical molecule, which one of those alpha hydrogens would we deprotonate? Yeah, why? Because it's the most acidic between the two. It's between the two carbonyls. Now, as long as you're doing aldol chemistry, it's really not useful if you have multiple hydrogen atoms. So we have to do what's a directed aldol reaction. Basically, what this means is that we restrict what forms an enolate. So for example, if we had this reaction, do you recognize what this molecule is? Yeah, pyruvate. The main point of a directed aldol is we have one source of acidic alpha hydrogens. So this, if we do an aldol addition, it'll just add right over here. And make this beta hydroxy compound first, but I just let that step out. The other way you do this is through acidity. So like with the Robinson annulation example we just did, we can have this and the Michael addition. So we do have this set and this set and this set and this set. But because we make one site much more acidic than the rest, it's going to favor that position over the other. So what do we do in directed aldol? We either we direct it through just one set of alpha hydrogens, or we control it through acidity. We make one thing way more acidic than everything else. Any questions about that? Does someone want to go get me water? Thank you. This is why it's nice to be a teaching assistant. All right, moving on. So this is the last couple of concepts I will cover for before finishing what I've prepared. So chapter 19 and chapter 20 were relatively straightforward. It's all about determining what is or isn't aromatic and some EAS reactions. So the main criteria, the criteria you absolutely must have, MUST. It must be a cyclic molecule. It must be hyperconjugated, or it gets to a state where we can form hyperconjugation. Thank you. and it is flat. Flat or planar. If it fails to meet one of these criteria, one of these is not met, then it's neither anti nor aromatic, it's just a non-aromatic. You know, it's called aroma because they used to smell because they smell good. But straight up benzene and toluene, it's paint. Have you ever smelled paint before? That's the smell of aromatics. That's what's in your paint. Now, Huckel's rule is what determines whether it's aromatic or anti-aromatic. What is Huckel's rule? Yeah. So it has to be 4n plus 2, 0, whoops, 2, 6, 10. Has to fit those specific number of electrons. If it's 4n, 0, 4, 8, no, not 0, 4, 8, 12, it is specifically anti-aromatic. And the reason for that is if you do the Frost diagram, you'll see that you'll have electrons in the anti-bonding orbitals rather than the bonding orbitals. So 4n in attempt to become aromatic, it puts electrons into anti-bonding orbitals. So that's a destabilizing factor. So if it's anti-aromatic, it'll break one of the first three rules in order to become non-aromatic. Any questions about that? We only covered that very briefly in lecture. Hint. So the main application this leads to is electrophilic aromatic substitution. And the shoe fits, wear it. So the general mechanism here is that you have the benzene ring or some other aromatic species, because this does work for anything that's aromatic. The rules we learned, ortho, meta, para, only apply to benzene or any other six-membered ring that has ortho, meta, and para positions. What happens is that a strong electrophile attracts a pi bond out of the benzene ring to give us this sigma complex. And then we just have our nucleophile, which attaches to that complex because that's an empty orbital. So we get, I put my double bonds in the wrong spot. And the key, wait a second. No, that's not what we do. We generate that positive charge, but the thing about this is it wants to regenerate aromaticity. So with this, we still have a hydrogen sitting on that carbon. What happens is that this gets deprotonated, leaving its electrons available to come down and regenerate aromaticity, like so. So all EAS mechanisms follow that. You have to have your strong electrophile, and you have to have some mildly basic species in there to regenerate the aromaticity. Now, this is where we get into some regioselectivity. And this all has to do with if it's an electron withdrawing group or an electron donating group. So it's an ortho-para director if it's electron donating. And the two ways we can donate our electrons are through induction or through resonance. So if you have something like a tert butyl group, The sp2 hybridized carbon is more electronegative than the sp3 hybridized carbon, so that donates electrons through its bonds into the ring. Now, resonance, it's an opposite effect. So with nitrogen, you would think, oh, I'm gonna pull away those electrons from the ring, and that's a valid way of interpreting it. But you have to remember that you have this lone pair which can easily dump into the ring. And since we have those electrons in the ring, that makes it much easier to do an electrophilic aromatic substitution. Certain types anyway. Orthopara. Now, meta-director is strictly for electron withdrawing groups. And this is mostly through induction and to a lesser extent resonance. So the king of all electron withdrawing groups is NO2, where we have this. So this one cannot resonate into the ring. Why? Why? Sorry, but what? Yeah, there's no lone pair on this nitrogen. So in this case, or let me choose a better example. Induction. This one has no lone pair. The ketone has no lone pairs to pull into the ring, to push into the ring. This can only withdraw electrons. Now going back to nitro group, I just wanted to do that to illustrate the induction effect more clearly. Now with nitro, it's an inductive effect as well, but because it doesn't have a lone pair, we can actually bring electrons we can actually bring electrons from the ring to the nitrogen and to the oxygen like so. So it is also with the effect is the same whether it's induction or resonance. It just depends on what's attached to the ring and where the lone pair of electrons is. Any question? Yeah. Yeah, because you're pulling electron density out of the ring. So whereas the electron withdrawing, we put those lone pairs into the ring, here we're taking it out of the ring. And for electrophilic aromatic substitution, we definitely want to get it out of the ring. You could probably liken this to the gladiators of ancient Rome. Get out of the ring, not into it.
Go over real quick the rules on like how it fits like your DR group and down like that.
Yeah, I will. Yeah, we'll just do it right now. So I'll cover the reaction first, then I'll just cover why it's the exception, so to say. Oh, yes. If it's electron donating, it's an ortho-para director. If it's electron withdrawing, it's a meta director. So some reactions you definitely want to keep in your toolbox are halogenation. So here we just take benzene. Whoops. We add the dihalogen and the iron chloride. We need the iron chloride as a Lewis acid catalyst to make the chlorine electrophilic enough. I'm not going to go over the mechanism. I'm just going to show you that it's a thing. And it also works with bromination. Now, the exception to the ortho-para directors are the directing effects are halogens. They're both more electronegative than the carbon. So in that way, it's deactivating. It's deactivating via induction. However, it acts as an orthopara director. But acts as an orthopara director. Why is that? Because each of these has a lone pair of atoms that we can bring into the ring. Now you will notice that these are weakly deactivating because this resonance form does not contribute a lot to the stability, but it does contribute enough that it makes it an orthopara director. So it's weakly activating, but an orthopara director. Other reactions you need to know. Nitration. This is probably one of the easier ones. But this is just simply taking the benzene ring, taking nitric acid and a stronger acid because we have to generate NO2 as our electrophile and tack it on right there. Now let's see, did I leave a slide for the workarounds? Yes. And let's see, what type of group is that? Withdrawing group, so it's an M director. Okay, the next one is sulfonation. Pretty much the same thing as nitration. Except what we add on, instead of adding on a nitro group, what we're adding on is SO3H. That's our electrophile. So what we get in the end is, I think that might have a charge in it, but I don't care. Now let's see, is that an ortho? What kind of director is that? Meta, yeah, it's a meta director. It's electron withdrawing. Friedel-Crafts acylation. So this one is when you specifically have a this is a unique one because this is where you have to use an acyl halide. And you have to have a strong Lewis acid such as aluminum trichloride to make that chlorine come off. Because what's our electrophile in this case is going to be this bizarre oxonium 1, 2, 3, 4 1, 2, 3, 4. This bizarre oxonium species 1, 2, 3, 4. And that generates this as our product. What type of director is that? Someone said it? Yeah, meta. Okay. Whoops, I didn't mean to do that. Friedel-Crafts alkylation. Alkylation is very much the same thing, and it's pretty much the same mechanism, but we have to be somewhat cautious here. Because what can happen here? Yep, we generate as our electrophile a carbocation-like species. But as you learned to know from 351, see, chemistry never goes away, at least in this class. You have the possibility of rearrangement. So if you want to make a, let's see, if you want to make a rearranged product or like a tri-substituted alkyl group, that's Friedel-Crafts alkylation will definitely work for that. But if you want to do a primary or secondary carbocation, that doesn't work very well, at least through the Friedel-Crafts alkylation mechanism. So for the work, oh yeah, and which one is this? Is it orthopara or meta director? Yep, orthopara. If you want to get a singly substituted, if you just want a straight chain alkene like this, you have to do a workaround. And since I'm here, yeah, I'll just do it right here. So the workaround for that is we have to do first a Friedel-Crafts acylation. Because that whatever that ion is called will not undergo a rearrangement because the positive charge will still basically stay on that carbon. But what you can do is do a Wolff-Kirschner reduction. Wolff-Kirschner, or you can reduce it with zinc. That will selectively reduce the ketone to an alkane. So if you want the straight chain, you have to do acylation, then reduction. You can't do alkylation because alkylation gives you rearrangement. Oh, perfect. That was a good transition. Yay me. Reduction nitro group, radical bromation. What's the other one? So this something you want to keep in mind for the acylation reactions or any Friedel-Crafts reaction is it will not work if you have the amine or the nitro group. Where's the other one? There it is. No. No. Okay. Why is that? Well, the nitro group is too deactivating to undergo any sort of Friedel-Crafts reaction. The aniline, the amino group on that benzene ring, is too reactive because it adds directly to the Lewis acid catalyst. Nitrogen is still very basic. And we'll talk about the basicity of amine groups tomorrow. Anyway, just some common workarounds. So the reduction of the nitro group is a super helpful tool because that gives us access to the aniline yet again. So how do we reduce the NO2 group? Yep, hydrogen, palladium on carbon. And this one, I'll just do this one right here. I did not make a separate slide. I made a separate slide for this one, but not the other one. This one, since the amine is too, if the amine is too reactive for something, we can actually do an amidation like this. We don't need any special catalyst because it's already reactive. This turns it into an amide. And this, because of the lone pair of electrons on nitrogen, it's still going to be somewhat ortho-para-directing. Less so because it can also resonate with that carbonyl. But look what that does. It takes away the if we wanted to do a Friedel-Crafts alkylation with this, we can convert it to the amide, then do something like this. FeCl3 and get to here. NH. And remember, it's a rearrangement. But anyway, the point is we attenuate the reactivity of the amine because now the electrons have to compete for resonance. And if we wanted to regenerate that amine, we could just do a hydrolysis. And the other thing you want to keep in mind, especially with this aniline, is a generation of a diazonium salt. And the special thing we do with that is sodium nitrite, because that converts it into this N2 plus, and this diazonium can either do another coupling, do a coupling like this. Let's see, I'll make up an example. Let's keep that like this. We can do a diazo coupling between another ring to form this compound, this type of compound. Or we could do a Sandmeyer reaction. This right here is an extremely good electrophile. So we could basically take any nucleophile, such as water or cyanide or even amine, ammonia, but that wouldn't really do us any good because we already had the aniline to begin with. We could do a chloride or bromide. So this is an alternative to to direct halogenation. This is an SNAR reaction. It has the same effect as SN2, but it's a different mechanism. Amine, I think those are all the, oh yeah, radical bromination. So I'm actually surprised we didn't actually cover any radical chemistry in this class. But this is unique because since this is a benzylic position, we can easily put a bromine group on there using light and just Br2. Allows us to put a bromine on there, and from there we could do, say, an elimination or a substitution. And I think there's one more. Yes, alkyl benzene to benzoic acid. So the reason we have all these workarounds is to change all the directing effects for our regioselectivity. So this one we can take toluene. The only case this doesn't work is when this alkyl group is tri-substituted. You need to have a hydrogen on there to make this work. If we take KMNO4, potassium permanganate, we can directly transform that into a carboxylate. It works with any alkane species as long as you have at least one hydrogen on that benzylic carbon. Okay, so we're right on time. Hopefully that was helpful. Let's I'll take a few questions now. Or we can just end it here. I don't know what you want to do. Yes?
Can you go over like, I know one of the exams we talked about the grouping of like our compounds, so group 1, group 2, group 3. Can you like go over those or like just tell me what they are?
Yeah. So this just goes back to what we did earlier with the reactivity of carbonyl compounds. So like acyl chloride, anhydride, acyl phosphate. Oh, and carboxylates on here too. Whoops, no, it's late. It's down later. So you just look at whether it's a good leaving group or whether it has a resonance. So like the chloride, the anhydride, and the acyl phosphate, that's basically group 1 reactivity. Thioester, the ester and the amide. Let's see, thioester. I say the thioester is in group 2 because it still has a somewhat good leaving group. The ester and the amide would be group 3. And then the carboxylate or the straight up just phosphate. That would be group 4. So you don't have to memorize specifically like, oh, this is like, these are all group 1 and group 2. It would be a question of like, which carbonyl compound is more stable. And you just compare the leaving group and the pK or whatever. Yeah.
The relation between these two has to be like wins when they actually screw this way.
Yeah. Irreversibility, yeah. Anything else? I've seen a previous copy of it. All right, I will stop the recording. Oh, hi, Andrew.